Well, good morning, everyone, and welcome to Ellensburg, Washington, USA. You're looking at the title slide for today's Friday at Noon talk, live from room 103 in Discovery Hall on the campus of CWU. Let's read this title slide together. Using Geophysics to Better Constrain Antarctica's Future Sea Level Contributions. Paul Winberry is a research associate here at CWU. He's up on the second floor, down at the end of the hall. Paul keeps a low profile, but he puts his head down and continues to work on these problems down in Antarctica. Looks like we're loud and clear. That's a relief. Thank you. Let me give you a sense of the room. Jordan Carey working his magic already. Checking in with a number of people. Lots of voices here. The spring weather is a big part of it. And let me get on camera here and say hi to a few of you. Hello, everybody. Hi, everybody, and welcome. I'm glad that you're with us live. We have 100 live viewers already, and this recorded lecture, if you're watching this in replay, Paul will be starting in about 10 minutes or so. And Hannah Shamlu, a professor here, is going to be doing the introduction of Paul here this morning. But as always, can we say hi and ask you, where are you viewing from before I turn the camera around and show you a bunch of folks in the room? We have a thriving geology department here, and I'm proud to report that, despite what's going on across campus and around the world, really. Pat the pilot from Natchez, Washington, on his lunch break. Hello, Pat. Ron Simpson. I was going to say, Pat, you're not here, are you? Peter is in Dayton, Ohio. Hans is in the Netherlands. Stefano is in Italy. Doug, Petersburg, Alaska. Elaine says hi from Tucson. Kevin from Fall City, Washington. Another Doug from Lincoln City, Oregon. Edgewater, Florida. Wichita Falls, Texas. Kingsgate, Washington. Sunny Orlando. Bothell, Washington. Garrett from the Netherlands. Yeah, I'm hungover, man. We celebrated last night. Mark, so I'm not doing my usual with you. Fort Vancouver. Michael from Trim, Ireland. Good evening to you and the family. Okay. Garrett, the Dutch Night Isle from the Netherlands. The Netherlands, the Netherlands, the Netherlands. I can do it. Nashville calling. Skagit Ed, Camino Island, Palatine, Illinois, Dallas, Texas, Yakima Valley. Okay, the person that typed in outstanding, I'm going to be keeping an eye on you. I hope you can pick up on the vibe of this room. I hope you can pick up the vibe in this live chat. I think you're new to us. You're welcome here. But please look around and take a temperature for the people here, including me. Thank you for joining us. Worcester, UK, LOL. Okay, wonderful. Well, thank you. Shortly before the top of the hour, we will put a second mic on Paul and make sure you can hear him okay, and then we'll be off and running. Thank you for joining us today. Give you another shot of the title slide, I guess.
Yeah.
You all set?
I said I would do it. It's on my to-do list now. I'm just hyped. Yeah. I will get it.
You're good.
Oh, Monday.
You got a good seat today. How are you?
Good.
Thank you for coming.
Wes is still doing good.
Good.
About an hour and a half ago.
Okay.
So we'll probably watch this tonight.
Good. Okay. Nice. You're back.
I am. Well, I'm here every Friday for this. Because I'm in 304.
Oh, you're in
But I would
304.
come anyway.
Good.
Because it's interesting.
Yeah.
Yeah.
Forgot your name.
Oh, it's Katriana
Katriana.
Keeler, yeah.
Wonderful. So you're going to continue with this in geology, do you think?
I don't actually. I've some financial stuff, so I think I'm gonna go back to work full time for a while. So, yeah, that's the plan. So I'll be finished at the end of March.
Okay.
Yeah.
You're graduating, or you're just kind of taking some time off school?
I was just taking classes because I wanted to take more
To get
classes.
a little
and
feel
sort
for
of
it?
Possibly career transition.
Okay.
But yeah, I think it's just not. It's a difficult time for it. Yeah.
Well, part of me wants to say, you know, we've got some really dynamic people. I don't know who you've been learning from this quarter, but anyway, I'm hearing what you're saying. So are you
Yeah.
going to stay in town, or are you going to move
No, I
elsewhere?
live in Walla Walla.
You do?
So yeah. I mean, I stay here while I'm right now while I'm taking classes because it doesn't make sense to commute 3 hours each way. But yeah, I live over that way.
Oh, wow. Well, thanks for giving us a try.
Yeah. Yeah, it's been good.
Good. Okay.
Yeah, it seems like a really good program here from granted my very limited experience. But everyone has good things to say about it.
Oh, that's good. Okay. Well, nice to see you again.
Yep, said that there wasn't a scale on it.
How's it going, Nick?
Good, Ryan. You?
We're good.
Yeah. How were the crumbs today?
Pretty good. No complaints here.
Fresh out of the oven. We've been working overnight. Got to get those just right for you.
The lab you make math.
That's what I like to do.
Class, the lecture is like
There's not a bad vibe in the room. Like usually people are pretty sour at this time of the quarter.
how math.
The weather helps.
Yes.
Yeah. So who's going outside later today or tomorrow?
Oh, absolutely.
Any place in particular?
We're going to up Cannon, the trail. So the trail for the ridge, you can go up left up the ridge, or there's like a shorter one, that's just kind of flat.
Yeah.
And we're probably gonna go on the flat one.
Good.
Maybe a bike ride around town later today.
Nice.
Get my bike or her bike fixed and that bad
Yeah.
tire.
Well, I'm sure the bike shop will be hopping this afternoon. Once that good weather comes, people will just swarm those places.
So for 351,
Yeah.
where are the field trips to?
Not sure yet.
Okay, fair enough.
Are you wanting to join us, or are you in the class?
I'm in the class.
Good. Good.
Yeah. And I was so I overheard it's going to be about cones. The cones. Okay. So yeah, I just was wondering where the field trips would be because we only have the X amount of hours or whatever.
Right.
Yeah.
I'll figure it out. I got a month to figure it out.
Exactly. You're fine. You're doing great.
All right.
I'm gonna do great. I don't know what. I do great.
Hi. Is our speaker out here someplace? Hey, Paul. All right. All right. Can I go right here?
Yeah.
And we'll have you talk to me or Audrey or somebody, and I'll just see if they can hear you okay.
Okay. Check.
Okay, viewers, if you can put in the live chat if you can hear Paul talking, please.
Product in it. All right. That's not biking.
Your wife's in the same thing.
Could you type
right.
Paul 5x5
All right.
if you can hear him? He's the guy standing there on the wall.
That's right. Let's see.
Thank you.
Oh, I
So
have,
excited to hear about
oh, thanks. Thanks. All right. Can you hear me? All right.
Yep.
Good. All right. Well, I guess Nick can, so that's what matters, I guess. And I guess he turns it.
I'm trying to remember. You gave a talk 5 years ago, maybe here? Or
Yeah.
Roughly?
I think it was only 3, yeah.
3.
Yeah.
But before we did this setup.
Yeah, oh, it was before we did the setup, yeah.
It's kind of we were kind of half in COVID almost. and
Yeah.
People were like watching from their office and
Yeah,
that
yeah.
kind of weird thing. Okay.
Yeah.
Remember how cool that was?
The good times, the good old times. Let's write a song
back to
about
that.
it.
Yeah.
Totally.
No, you gave a talk though when I first started here, and it was really awesome. So I'm excited for this. It's like an
All right, let's see. All right.
Okay, I'm gonna
I don't
turn
have
on.
any kind of title. Oh, is those the titles for spring on that board or no? We're not going through that. Okay, this one.
I shot an email this morning, Nikki canceled. So the whole
Back to
thing's
the
in
drawing
flux.
board.
I mean, I don't know, man.
That's all right.
Might be us doing talks again this. All right. What in the world? What in the world? You guys have quieted yourselves. What was your cue? I don't know, but you're dead silent. There was all sorts of life in the room. I'm going to keep playing with the audio here for just a second, and then I'll hand this to Hannah. How am I doing? Is this strong enough? Just about right? Especially if I get away from the amp. Thanks for coming.
Hi, all. Welcome to our last seminar talk of this quarter. Next quarter, we have a really awesome lineup. I don't have any titles to read to you, but hopefully you got Nick's email. We've got a lot of exciting speakers coming up. So this is Paul Winberry, our very own CWU Research Associate. He was born in North Carolina, so he came a whole long ways to be here in Washington. Fun fact, he was in Bishop, California in 1999 when CWU was teaching 210. So they overlapped, actually. So his fate with CWU was locked since 1999, which is pretty cool. At that time, he was an undergraduate at UNC Chapel Hill, where he got his BS in geology. Then he moved on to get a MS, a master's, and a PhD at Penn State. And then in 2008, he started at Central Washington, and he's been here ever since. So we're very excited to have Paul talk to us today about Antarctica. So please help me welcome Paul.
All right. All right, thanks. It's really great to be here. It's a really strange time. To be a scientist talking about science. It's a bit like picking out wallpaper while the house is burning down, but we're going to give it a go. All right, so I've done a lot of work in the past 25 years, basically in cold, icy places. Done some work in Alaska, Greenland, Norway. Today we're going to be talking about Antarctica. I've done about 16 research trips down there doing various kinds of geophysics. And today we're just going to focus on a few little sort of small parts of a couple of those projects to give you an essence of how we use geophysics to help understand the movement of ice and their contribution to sea level in the Antarctic. All right, so a little geography for people who, because a lot of times Antarctica gets smushed down to the bottom of the globe. It's a big place. It's bigger than the continental United States here for comparison, and it has about 60 meters worth of sea level equivalent of ice stored up there. If you just took it out and spread it out over the ocean, that's how much ice sea level you would get to rise. And in our brief instrumental record, the satellite record that goes back to like the 60s and 70s and on, we know that right now Antarctica is losing ice, losing mass, and that's raising sea levels, along with thermal expansion of the oceans because we're trapping heat in the ocean. That's where most of our heat gets trapped, and we're melting glaciers and Greenland as well. And so we'd like to be able to understand how fast that's going to accelerate in the future. And so this is from a recent paper just out a few weeks ago in Science by Helen Fricker and some other good colleagues. And basically what you see on the sort of right, that side of the graph, is the y-axis is global sea level just from the Antarctic, not Greenland, thermal expansion, other sources. And then we're looking at sort of projections into 2100. And then you can see there's this, and each one of those lines is a different model with different assumptions. These are all usually run with the exact same forcing. So this is just model physics because we don't know how to parameterize the physics. And you see by the time you get out to when people who are young now will still be alive, you can expect up to a third of a meter of sea level, or a foot, just from the Antarctic. And then by the time you go out to 2300, the y-axis is changed, and it just goes off the charts. And so this uncertainty basically stems from the fact that we don't understand all the physical processes that control how mass is transferred from the grounded ice sheet into the ocean. Okay. All right. And we see projections like that, and we think about sort of the entire ice sheet collapsing into the ocean. But I just would like to remind people that even very small changes in the amount of ice that we have tied up in land, whether it's the Antarctic, Greenland, Mount Rainier, when we transport that into the oceans and raise sea level, really small things can have significant impacts. So I'm from, as we mentioned earlier, I'm from eastern North Carolina. That's where I grew up, is if you take 2% of the ice that's on land right now, shove it into the ocean, where I grew up is a completely different part of the world, and my commercial fisherman family would have to build new docks and all those kinds of things. So small changes can have big impacts. I think that's one thing. And then, so the next thing I want to talk about is how, and this is what we're going to talk about most of the rest of the sort of 50 minutes or something, is how Antarctica is losing mass into the world's oceans. So you'll see headlines like this: Antarctica is melting 3 times as fast ago as it did a decade ago. And that's not quite right, because Antarctica, when we think of sort of ice cubes, we think of glaciers, we think of them melting like physics from the air. But actually what's happening is the glaciers that feed into the ocean are actually accelerating. And just to bring that home, if you've ever fly to London from Seattle and you wake up, pull up your shades, and if you look out the window at Greenland, you'll see something like this in summer, and if it's daytime. And we're looking at the surface of the Greenland ice sheet from a transatlantic flight. And what these are melt ponds on the surface of the ice sheet. So it is the atmosphere is warming, and we actually are melting the surface of the ice, and we're transporting mass into the oceans by melting. But that's not what's going on in the Antarctic. The Antarctic looks like this. It's still, the surface temperatures are still really cold all the time, except for the very tippy tops. So most of the ice sheet always looks like this. It's just flat white snow. So how is the Antarctic contributing mass to the ocean? And before we talk about that is some bit more of geographies to think about, is when we think about the Antarctic, what we've done now, this is the Antarctic continent. Remember, this is really big, bigger than continental United States. And what we're looking now is a map of the bedrock elevation. So if you take all of the ice off of the ice sheet, what does the surface of the Earth look like under the ice? We've got kilometers of ice in Antarctica. And so what you see is we have this really rugged landscape. We have mountain ranges. So this is right here is the Transantarctic Mountains that actually poke out in many places. We have the Gamburtsev Mountains. These are about the size of the Appalachians, and they're completely covered by ice. But the other thing to notice is a lot of this area is below sea level. So even though the ice sheet is above sea level because it's so thick, it actually stays grounded because the ice is so thick. And so that's really important when we think about Antarctica, is we have all of this ice that is sitting on bedrock below sea level. And so then if you start to take a cut through the ice sheet, and we think about it, you get something that looks like this. So on the left, we have the ice sheet. On the right, we have the open ocean. And of course, in the middle, we have an ice sheet there because it snows and it doesn't melt. But then the ice gets thick, and it wants to flow out towards the ocean. And when it gets thin enough, it'll eventually form the floating ice shelf. So we'll keep those two terms distinct. Like ice sheet is something the ice is actually sitting on bedrock, and ice shelf is glacier ice that's flowed towards the coast and is thinned. It is now floating. So it's already contributed to sea level, but it is going to play an important role in our story. And so what you can see now is because this ice is grounded below sea level, it actually comes in contact with the ocean. Okay? And what's going on in Antarctica is that as we have these floating ice shelves, and these are important because they actually push back on the grounded ice and help restrain it a little bit. But we're warming our planet, we're warming our oceans, and some of this warm water is actually making it into these cavities underneath the floating ice shelves. And actually what's happening is instead of melting our ice sheets from above, what we're actually doing is we're melting the ice shelves from below. And when we melt those ice shelves, what they do is they thin. And then what that does is that retreats the grounded ice further inland. And that's really important because then what happens? We all know about gravity. So now you have this retrograde slope here. You have this deep interior. And so then what happens, you've retreated. Now you have thicker ice where it goes afloat. And thicker ice wants to flow faster because ice is going to flow under its own weight. So that's how the gist of how ice is being lost. Most, like 90% of ice is getting lost in Antarctica today. Okay. So yeah, we retreat because we're warming the oceans. It gets under there. The ice moves faster. Okay. So that's the process. But what we really want to know is that we came back to that first slide. We want to know sort of how fast this will happen and by how much. So we need to know how much warm water is going to get under there, the physics of melting, which is actually really complicated because fluid dynamics is really hard. We're not going to talk about that. And when the ice shelves get smaller, we see this retreat. It's going to speed up, but how much is it going to speed up? And these are all questions that geophysics can play a part of, and we're going to just touch on a few parts of those areas. Okay, so the first way first thing we're going to touch on is we're going to look at, like we said, is sub-ice shelf bathymetry, understanding what the ocean looks like. The shape, just really simple, what does the shape of the ocean look like under these floating extensions of our ice sheets so that we can do better oceanography, or other people can do better oceanography, not me. And the next thing is on the response side. Once the ice sheet comes off these ridges and starts to retreat, the ice wants to accelerate. But how fast this ice is going to speed up depends on what's going on underneath the ice sheet where the ice meets the bed. Okay. And before I go into where we're going to study, I'll just show this map now. This is a satellite-derived map that came out a few years ago. Once again, what we're looking at, here's the Antarctic continent. And anywhere you see the red and blue colors, those are the floating extensions of the ice shelf. So we have all these ice shelves fringing around the Antarctic continent. So this white is the grounded ice sheet, whereas this right here, this is the Ross ice shelf. This is the biggest ice shelf in the Antarctic. That's the size of Texas, or if we were in Europe, you would call it France. But basically, you can see. But then you have these places where there is lots of red, and those are places where these floating extensions are melting really fast. And then what we have in green is the thermal forcing. I'm pretty sure in this case, it's temperature above freezing. So this is basically how much energy is there to melt the ice shelves. And what you should be able to see is that places that are where the ocean, the continental shelf here, is green, you have lots of red ice shelves. And basically, like sort of the Ross Ice Shelf here, isn't melting very much, but it has relatively cold water flowing in underneath it. So we have this connection between basically a thermal forcing from the ocean eroding the margins of the Antarctic continent. And we're going to look at, first, we're going to look at the sub-ice shelf bathymetry of the Totten Ice Shelf, which is this glacier right here in East Antarctica. We're going to do that first. And then in the second half of the talk, we're going to move to the other side of the continent, and we're going to look at the Thwaites Glacier, which is over in the western part of the continent. And you'll see the reason, just before, because if I say this again, in the Antarctic, we think of east and west because this is a general projection. So in this projection, England is due north. And so basically everything on the left side of the map is west, everything on the east side this side is east. So even though everything's north, north is everywhere. Okay, so let's just come back to this bathymetry and why do we need to think about the bathymetry beneath these floating ice shelves if we're going to do oceanography. And this is a simple cartoon I grabbed this morning, and this is from a fjord. The same idea works under an ice shelf. But basically what we're looking at is on the x-axis we have distance from a glacier front. This is trying to simulate a tidewater glacier in Greenland. And the y-axis is depth and the x-axis is distance. So we've got like 20 kilometers by 500 meters. And what we're doing here is trying to model the ocean circulation in this fjord. They are trying to model the ocean circulation in the fjord. And what they've done is they've done some experiments here where they put a big bump at the front of the fjord. At the top, there's no bump. Here, there's a pretty high bump, and here's a really super high bump. And that's what the gray is. These are just bumps of sediment, sills. And in these model simulations, the yellow is kind of very warm, so it's going to have a lot of energy to melt the glacier front. And blue is cold. And so what you can see is if you put big geometric obstacles, not surprising, the water can't get through and melt the front of the glacier. So understanding just the generic shape of the bathymetry underneath your floating ice shelves is important. And the other thing, which we're not going to talk a lot about today, is that if you have these big bumps in front of your glaciers, basically what happens is the ice exits the ground and it becomes an ice shelf. It can get hung up on really high pieces of topography. And when the ice shelf gets hung up on these really high pieces of topography, they have the ability to sort of basically push back and provide a buttressing effect on the grounded ice. And that will slow down the ice. So if we have warm ocean that's coming in under the ice shelves, melting the ice shelves from below, not from the atmosphere, what can happen is they can thin and then they can lose contact with these pieces of high topography, and then the glacier will want to accelerate. And we've seen that in certain parts of the Antarctic. Okay. And this is a really nice comprehensive review of this in the last few decades. Just came out in Nature. Okay, so first, all right, we're going to go over to the Totten Glacier. And what we're looking at on this map is a map of flow speed, satellite-derived flow speeds. And what we see is these purple colors and blue colors are places where the ice is moving, sliding hundreds of meters a year. So you actually see this very segmented structure and surface velocity. It's not just this big stagnant piece of ice. We have these little rivers of ice, like here's the Totten Glacier, and then you see that go up there. These are what we call ice streams because they're not bounded by rocks. They're bounded on ice by either side. And again, there's the Antarctic map up on the top there, and we're just looking at this little red box. But this single glacier, Totten Glacier, the reason we went to study it is because it's what's thinning. It seems to be not 100% stable, and it drains this one of these very large subglacial basins that it can retreat into, as we discussed earlier. And just this single glacier, if you just look at the catchment basin, all the ice that flows out into the ocean through this one glacier, this glacier contains enough ice to raise sea level by about 3.5 meters. All right. So, and what we're going to talk about is, if you're curious, we just published this with some colleagues in GRL. Basically, we're going to look at sort of updating the bathymetry below the ice shelf of the Totten Glacier to see if we can understand the spatial pattern of melt at this ice shelf. And this was work that was primarily funded with Australian colleagues through the Australian Research Council, and we used some equipment from the SAGE facility that NSF funds and is operated by the EarthScope Consortium. All right, so now we've zoomed in again on this Totten Glacier, and what we're looking at is now, what's the scale here? Like 50 by 60 kilometers, or 100 kilometers. So we've zoomed in and we're looking at the bed topography. Again, this is what the shape of the Earth looks like when you take the ice off. And you see it's actually quite sort of rugged landscape, yeah? Like the scale here, this is meters below sea level. So the deepest parts are 2,000 or 2 kilometers below sea level. And there's ice that's like 3 kilometers thick, right? And, but then we also have this surrounded by mountains that are, hundreds of meters above sea level. And of course, this is all covered by ice. And this white line that you see here is the transition from ice that's stuck on the ground and then this becomes the ice shelf, all right? And so the next slide is we're going to zoom in and just look at, from satellite-derived estimates, basically how fast are we melting the underside of this ice shelf. And so the way you do this is if you do repeat satellite altimetry, right? If you have floating ice, right? It's like an iceberg, there's some more complications to this, but the basic idea is, right? 9/10 of an iceberg is below the ocean, right? And so if you come back by many times with a satellite altimeter and the elevation of this floating ice changes, you can estimate the mass loss of that floating bit of ice. And so that's what we're seeing here, is in all these colors are the places where the ice is floating. And if the ice was in steady state, as much ice was coming in as going out, this would just be a really boring plot, and it would be, everything would be blue. Basically, that means no melting. But we see places right where it goes afloat, near the black line, the grounded ice, we can see places where it's over 20 meters a year of ice is being removed from the bottom. Remember, this is where we're worried about, because as you start to remove this massive amount of ice where the ice goes afloat, that's going to promote retreat of the glacier inland. Okay, so we want to understand how this is possible. And so then, with colleagues, what we looked at, you start looking at before we started the study, the existing estimate of the bathymetry in this region. All right, and so up at the top of these sort of bunny ear patterns, near at the top of this floating ice, basically, remember we had really high melt rates, like more than 20 meters a year. But when you look at the bathymetry, and so what we're looking at here is not the bathymetry, we're looking at basically how much water there is between the bottom of the floating ice shelf and the ground, okay? And in some places, if you come down here, you have a 2 kilometer thick water column. So it's massive, right? There's this deep hole. But then what you have is if you look on the sort of the grid west side of this map, where I have highlighted in that oval area, you basically have a region where there's essentially no water column. So this is similar to the slide looked at a few days ago. There's this big bathymetric high that isn't allowing, if this is the world, you would not be able to get water from the open ocean in towards the grounding line to provide this thermal forcing to melt the glacier. And so we wanted to investigate this more in detail and see if we can understand is this really what the world looks like under the ice shelf. All right, and so how do we measure the shape of the Earth beneath ice shelves? Beneath grounded ice, the way we do it, or colleagues in the glaciology communities, we have airplanes. They put radars on them. Radars can travel through ice. The radar signal can come back, and you can measure how thick the ice is. But when that ice is over floating water, that doesn't happen. The water goes through the ice, but then it can't penetrate the water. So we have to rely on other geophysical methods to figure out the shape of the Earth beneath these floating ice shelves. And one way to do it is we go out and we take geophones and we lay cables and we do seismic reflection measurements. This is really laborious. We set off explosions and we basically just measure the travel time through the water. And so another way, but this is really slow. Another way you can do it is the same airplanes that have radars that measure the thickness of the ice. And this is the airplane fit out with equipment from the University of Texas, Austin. They do a lot of this work. In this particular slide, they were working with the Australians, but they have radars. So that's what these things are on the wings. These are radars. They send radar waves down, measure the ice thickness. But they also carry a gravimeter on board. And when you're over floating ice, basically, water is less dense than rock, and we'll see that in a second. And you can estimate how much water is beneath the floating ice from a gravitational anomaly. Okay. So those are the two main ways. You can also stick robots under there, but those are really expensive. And you can use SILs to get estimates. You can put little trackers on them. But for the most part, these are the two primary geophysical estimates. OK. All right. And so this is what you do if you look at gravity data from bathymetry estimates, basically the shape of underneath a floating ice shelf. And so what we're looking at here is just a 35-kilometer segment flight line. Now we're looking in 2D. And we're actually going across the floating Totten Glacier. And what we have in the top is the gravity anomaly. That's in milligauss. And those blue things are the observations. And at the bottom, we have a sort of a cross-section of what the Earth looks like in this area. So the blue is the ice. This is bedrock. And what it is to match the gravity signal, we need to have water underneath the ice in this part of the world. But you can see, depending upon what density you use for the gravity, right? Rocks have different densities. You can basically get, if you have really low density rocks, you can get, a few thousand meters of water. If you have really dense rocks like crystalline bedrock, you can get, a few hundred meters. So it's really important to have independent constraints on the geology underneath the ice shelves. And so the way we do that is by combining these seismic measurements, which are laborious to make, and we can't make very many of them, with these airborne gravity measurements that you can make in seconds, minutes, flying across the glacier. And so that's what we did. And so for this area in the Totten Glacier, to improve the bathymetry estimates, we went out and we made seismic measurements. And we also utilized some new airborne geophysics that had been collected since the previous initial estimate of subice bathymetry. And that's what we have in this map here. So here's was the existing bathymetry in the region and topography where it's grounded. Again, ice is flowing top to bottom. Everything in the black outline is floating. And the previous estimate of bathymetry was just made with those white lines. Okay, and then we were able to incorporate 3 new purple lines. So we have more airborne gravity data. But almost as important is we have these white dots where we were able to make these point measurements of water column thickness using seismic measurements. And you'll see that purple, that oval again is where that bathymetric ridge is that appears to be inhibiting the access of ocean water toward the grounding line, where we observe this really big melt. And so we really want to understand, is that a real feature or is it an artifact of the previous model? Okay. So how do we, just because we want to see some pictures, how do we do seismic measurements in Antarctica? We do them in a lot of different ways, but for this kind of study, we were really just wanting to fly around and get point measurements of the water column thickness. So we tend to use really small explosives. So here's Maddie. Basically, this is basically TNT. There's some det cord with a little detonator in it, and we're just going to sling that through, and we're going to set it off. The movie works. And we lay out some geophones, and we set off a little explosion. It's never, if there was sound, it's really unimpressive. People are really just, this is like this cycle of pop. But anyway, so that's what we do. And so for this experiment, and this is great, there's the smile. and so basically what we did is we packed up, we have a 200-meter long cable of geophones that we stretched out. We dug holes geophones. We put a really small explosive charge in the ground, lit it off, packed up, got back in the airplane, and went on. All right. Okay. And then you get some data that looks like this. It's a really simple geophysical measurement. People have been making these kind of measurements for, on glaciers for, almost 100 years now. But basically what it is we're looking at, if you're not used to looking at seismograms, the y-axis is two-way travel time. That's what we measure in seismology. The x-axis is offsets of geophones. So basically what it is, at location 0 is where we set off that little tiny explosive. And basically the sound wave travels down, comes back. It first hits off the bottom of the ice. Then it travels through the water column, comes back, and you get another echo off the bottom. And then you're just measuring the time it takes for the sound to go back and up, and then you have an a water column thickness estimate. You also have an ice thickness estimate, but there are much better ways to do that. Okay. And so then we did that. We combined our new water column thickness estimates from seismology, which provide us constraints on the subglacial geology, provides us constraints on density contrast, because we can pick between those different density models. And we were able to update the bathymetry. And what we notice is that on the left was the original water column map, where we had this area, that white area, people can't see this, right here, where there was essentially no water column. The ice was almost grounded. But what we can see is after with the new data and new analysis of the existing data, basically that was largely an artifact of a data gap. And basically we see that we still have quite a large thickness of water there, so that water from the ocean can make it through this gap and get to the front of the glacier. Okay. And just says the same thing. We now know there are pathways to get water from the ocean to the grounding line of this glacier. All right. Okay, so that's the first little vignette of how we use geophysics to understand glaciers. We're just basically measuring the shape of, a lot of geophysics in the Antarctica is just measuring the shape of things. We need to know how thick the ice is, what the bed looks like, so that we can actually then feed that to numerical modelers so they can do clever things like make predictions about the future. Okay. So now what we're looking at is another satellite-derived product, and this is from NASA. This is measuring mass loss using gravity, but now from satellites. So we were just looking at gravity from an airplane. So this is a whole different scale. And this is now basically time-lapse gravity. So in the previous map, we were just looking at a static snapshot. But basically here, NASA has these satellites flying around. They've been flying around for about 20 years now. And you could actually measure the weight of the Earth changing through time, which is pretty amazing, right? And by essentially measuring the weight of the Earth through time, you can figure out where the Earth is losing mass. And that's what we're looking at here, is basically where you have red, those are the regions where Antarctica is taking mass that was locked up in ice and dumping it into the ocean. And you can see that there's one region that's way, way, way redder than everywhere else. And there's only one place that really matters right now. Maybe not for the future, but definitely now. And that place is called Thwaites Glacier. And that's what we're going to talk about next. The challenge with Thwaites Glacier is that it's really, really out in the middle of nowhere. It's really hard to get to. So the main US Antarctic base is right here. It's called McMurdo Station. And that's accessed via ships and airplanes from New Zealand. And there's nothing in between. And that's like over 1,000 miles. So it's really hard to get to. And so to study this part of the planet is really expensive. And so as Anne sort of introduced last week, when you need a lot of money to do science, and there's limited money to go around, NSF goes to the community and says, tell us where to spend our money. And so about 10 years ago, this National Academy of Science and Engineering report came out, basically said, where should NSF be spending their money in the Antarctic? And this was a really long process, starting in 2013, 14. The group of people who led this document went around to UW and other universities. And I actually went to one where they asked community. There were these workshops where you just sat around and said, where do we want to spend our money? And they came up with 3 priorities. One about how things live, and one about how the universe began. But the first priority, strategic priority 1, was basically how can we better understand ice loss from sort of the Antarctic ice sheet. And what that resulted in 2 years later was NSF joined up with the Research Council in the UK, that's NERC, to have this joint solicitation where we're going to spend a lot of money and spend a lot of effort trying to go to this really hard place, see if we can better understand Thwaites Glacier and its contribution to future sea level rise. Okay. And in the end, what happened was this collaboration called the International Thwaites Glacier Collaboration, again, primarily funded by NSF and NERC. And along the way, we also got some more international partners. There's many more than shown here, but the South Koreans, Sweden, and Germany made significant contributions. And there were the 8 projects as part of this big initiative. And the main thing about this is there's me up here, but science is people. This was 8 projects. And if you go to, there's this website where you can learn more about Thwaites Glacier. It has lots of fun infographics, thwaitesglacier.org. And if you look people and you just keep scrolling and scrolling and scrolling, there's just hundreds of people. And I'm pretty sure this is still just probably half of the people involved. And this is where I just want to say, science is people. And our house is burning down right now, right? And I think as scientists, we need to recognize, and we need to stand for this, that sort of diversity, equity, inclusion is fundamental to our healthy science ecosystem. Here's a boilerplate statement. You can read it. This came out from the Royal Society a few days ago. But basically, there is no science without people, and there is no anything. We can only do our best if we have everybody coming to the table. And I was really excited. So this ITGC project, that stands for the International Thwaites Glacier Collaboration, we did made some really significant steps sort of to making polar work, which historically has been not very diverse, not very equitable. It's not been a very nice place to work for many people. And you can Google and find nice stories about that, not nice stories. But we did a lot of simple things, that we should be proud of, like during our in-person meetings, right? We had hundreds of people involved in this project. When we had these in-person meetings, we had special breakout sessions, DI sessions, that were moderated by a professional where we discussed our challenges and shortcomings. And it wasn't confrontational. It was everybody dedicated to making the community better. We generated documents on best practices. I wasn't, but the people who led these efforts did amazing jobs. Just like when you go to the field, talk about expectations and responsibilities and creating pathways. And a lot of this sort of spills over into just general field work anywhere on the planet. It doesn't have to be polar. Polar has some unique problems or issues, but it's really about creating a community where everybody feels welcome and can be successful. And I think, and so I'm really proud to be involved with this project because I think we did a lot of really good things. Okay, so as I said before, this is really complicated. Where we wanted to go do science is way out in the middle of nowhere. And it took a lot of different countries working really hard. And this is a really complicated graph. And it's good, because it is because that's just, you can't read it all, but it's really complicated. So impactful science requires people working across boundaries. And so this was the initial 4-year plan for this project. So remember, we had a National Academy report in 2015 saying Thwaites is important. 2017, there was a solicitation, I think there were like 15 proposals, 8 got selected, and now we have our science ideas. We have to actually go and implement it. And so it's supposed to be 4 years. And I really like this. It's like down here it says, nobody can read this, but it says subject to revision. So in year 1, but basically the point being is like we have all these ships because we were going to study the glacier from the ocean. So we need ships, and ships are expensive. So the red boats are British boats. This black boat, that's a South Korean boat. These grayish boats, those are American boats. And then so we got 4 years, and we got boats coming from all different countries. Boats are expensive. Oh, and then because we're so far away from everywhere, we need airplanes to take stuff. And so there's white airplanes coming from Team America, red airplanes coming from Team UK. And then, so it's sky, sea, then land. Then we're going to drive tractors around and do stuff over land. So it's really complicated logistically. No one country can do any of it. Okay, and of course then COVID happened, and this got revised, and our 4-year plan became a 7-year plan. And the project I'm involved in, we actually didn't get done with the field until like 12 months ago. So I'm not going to have a lot of results because we're still trying to figure what we got out. But basically, COVID made everything complicated. And we still had lots of boats. Actually, it was really funny. The boats, the ship marine part, was actually the part of this really complicated project that was least affected by COVID. The most expensive and complicated part actually went through. So there's no boats in the latter part of the project, just more airplanes and sort of tractor trains going across the surface. But the point is this really complicated logistical chain, right, is not going to be professors at universities calling up to the phone saying, can you get me my $5 million boat to go from here and there? No. All of this complicated logistical work is dedicated civil servants working really hard, making connections across boundaries. And right now, we're taking, and a lot of those civil servants, they're not paid poorly, but they've made decisions to work for lower salaries than they could in private industry. And there's a trust between the government and science. We can have a discussion about how much we want to fund science. We can say we need to have less science funding. That's fine. But we need to do it thoughtfully, and we don't need to destroy sort of this rich ecosystem of trust that we've developed over the last 7 decades. And so right now, for example, I have a project which we're supposed to be going to the field in 8 months in Antarctica. Once again, another large international collaboration. We've got Germans, Japanese, New Zealanders. Right now, there's nobody at the United States National Science Foundation I can call and ask them about my project because that person was fired last Tuesday. Okay? And there's nobody to replace it. And just because of the vagaries of staff turnover, that person happened to be hired permanently recently. So, it wasn't thoughtful. And so I just want to say, these cuts, we can discuss how much money we should be spending on science. I think it's fair game. That's a political decision. But we're basically tearing apart our ability to do science in this country. Okay. So, but before all that happened, with the International Thwaites Glacier Project, these great civil servants were able to sort of take us from sort of the COVID world and get us into the field. And so we had all these projects. We had people studying ice. We had people studying ice atmosphere, ocean. We had geologists on land looking at sort of moraines to figure out how much the glacier had thinned and changed in the past. We had people getting Marine Corps. So there was a lot of really great science. And so I was involved in this red box there, was called the GHOST Project, which stood for Geophysical Habitats of Subglacial Thwaites, because they wanted us all to have acronyms. But we had, so our part of this project was basically, will basal conditions under the grounded ice sheet allow the rapid retreat of the grounding line? Okay. And so as remember, we talked about earlier, so it's the ocean side. We're getting warm ocean water under the ice shelf, and that's causing the glacier to move back. But then, and it's going to want to accelerate because we've got thicker ice, but how much more it will accelerate is related to the subglacial geology. And to do that, I just want to have a really quick cartoon remind us how glaciers are getting off the ocean. Okay, so some people, when they think about ice in Antarctica, they think it's really cold. But actually, under sort of kilometers of ice, you can actually have a very wet environment because you have so much ice, you've changed the pressure melting point, and you can collect water at the bottom of thick ice sheets. That has nothing to do with the surface. We're just melting millimeters a year. What happens is if that water can find its way into some dirt or till, basically that acts as a lubricant and allows the glacier to slide. So most of the ice that we see getting off of the continent into the ocean is sliding. So the deformation of the ice actually doesn't matter that much. But places where, and so this is a cut through again, the red vectors are basically supposed to be showing fast moving ice, right? And so if you go over this side where there isn't any till that has some water in it, basically it's stuck because there's no lubrication, so the ice doesn't want to slide over the bed. Okay, and so basically at the end of the day, the spatial pattern, we showed that really nice picture of Totten where you had slow ice, fast ice. That pattern to a large extent is controlled by the distribution of subglacial geology and subglacial hydrology. Okay, and this matters because you can do your simulations of future ice sheet retreat, and this is a case for Thwaites. So in this slide now, the x-axis is 250 kilometers long, and we have two sets of simulations. The y-axis is elevation going from minus 1,500 to 1,500 meters. And these two model runs, so ice is flowing from left to right. So this is our ice shelf. This is open ocean. The only difference between these two sets of simulations is going to be how you prescribe the bed. Is it basically hard rock or sediment? And so both of these model runs start with the ice sheet in green. So you have this advanced ice sheet, and then you change the atmosphere of the ocean to sort of, and you want to see how this thing responds. And what you'll notice, and the red is the final model position. You'll see the top model run has completely run to the edge of the model bin. The glacier is basically gone, and all you have essentially is a floating ice shelf. Whereas down at the bottom here, what you see is there's a little bit of retreat, right? But the glacier didn't really move that much. Everything's exactly the same. The physics of the ice, the temperature forcing, it's just basically, do you have dirt or do you have rock? Right? That's right. So And that's a pretty simple, well, it's not a simple thing to measure. Because if we peel back the ice again, another way we can look at what's underneath the ice sheet is we can take the surface velocities and estimate basically where resistance is being provided under the glacier. And this is Thwaites now looking at a different view. Sorry, now we're switching the map again. But the ice is flowing from up here, down here. Here's the open ocean. Here's this ratty ice shelf that sits in the front of the Thwaites Glacier. And basically, blue bits are where the glacier is really slippery. Red bits are where there's something, whether it's the hydrology or the geology, is providing resistance to motion and is basically making the glacier not want to flow faster. And we need to understand this pattern so that we can determine which of Byron's models is correct. All right. And so to do this, we had originally proposed 2 8-week field seasons back in the before times. In the end, I think we got like 2 3.5 to 4 week seasons. So, and so we did a whole bunch of stuff to try and characterize the subglacial geology. We did explosive source seismology, similar to what I just showed on the Totten. Our German colleagues had a vibra-sized truck that they towed around. They've got some great videos that if you go to the thwaitesglacier.org website. We did some magnetotellurics, we did some passive source seismology, we did a bunch of radars. So we did a lot of geophysics. Here's just one experiment that we did. We zoomed in again on that previous map where the colors basically show how slippery the bed is. And so red is really sticky. The ice doesn't want to slide over quite so easily. And blue is a little slipperier. And so one of the things we did is, like, all these little dots are seismometers that we put out for like a month to measure sort of really small earthquakes that occur as the ice slides over, so we can measure where the stickiness is. And we're also recording earthquakes to try and figure out the sediment distribution beneath this array. Can we understand the transition from sticky to slippery across this boundary? And the way we do that, and this is what I do, we're running out of time. But basically, one of the things we do with these seismometers is we record earthquakes. Basically, over on the side of the left side of the screen is a simple little cartoon. You have ice, sediment, bedrock. And basically, if you record an earthquake coming from somewhere on the other side of the planet, if you have sediment sitting under your glacier, basically the energy traps around. And you can use this bouncing around of the earthquake waves, which is what's on the right, which is a seismogram, a few seconds of a seismogram recorded from a distant earthquake. And you can use that to map out sediment thickness underneath the ice sheet. And that's what we're starting to do. This is just part of the way that we're trying to sort of figure out where we have sediment, where we don't beneath the ice sheet. And right now, it looks like in this one area, maybe we have sediment everywhere. So it's probably something to do with hydrology. OK. So just to sum up, Antarctic ice is being eroded around the edges where it meets the ocean. It's about that interaction between the grounded ice, the floating ice, and the ocean. And then the response once you've come off of any sill or any bedrock high and you start receding into regions of thicker ice. OK, and geophysics is going to play a crucial role in determining the boundary conditions of ice sheets. And lastly, I think we all need to remember, without people, there's no science. And we've got to take care of our people. OK, thank you.
Thank you, Paul. Questions for Paul, and Paul will repeat your question each time for the home viewers.
All right.
Yeah, I believe I read, a couple years ago that there were some volcanics on the west end of Antarctica. Is that okay? And if it is, does that have some effect on it?
Yeah, no, that's true. I mean, this is like one other. So Audrey Huerta, who's sitting.
What's the question, Paul?
Oh, that's right. I got to repeat.
You're good.
I
You're
didn't
good.
do a good job.
You're good.
Oh, he's. And so the question was, essentially, again, it's another component of geology. Does volcanoes, and in essence, geothermal heat flux, matter to the bottom of the ice sheet? So that's a fundamental question that another part of the research I do is focused on, is basically geology influences the stability of the ice sheets in so many ways. And one of them is, basically, as I said, if we go back to this figure, let's just see. Oh no, the figures are gone.
I got you.
Yeah,
Right
so we have this swamp under the ice sheets, right? We have all this water. And so that water, right, comes from pressure melting of the ice. It comes from sliding. But at the end of the day, you still need geothermal heat to help melt that ice and create that water. So a big part of sort of the solid Earth geophysics community's efforts in the Antarctic is exactly this, to try and figure out ways to map spatial variability and geothermal heat flux, because the western part of the continent is actually sort of an old rift system, so we expect there to be elevated heat flow and volcanoes, and there are active volcanoes in the Antarctic and in the region. And so just figuring out how extensive those features are under the ice sheet is something we're still trying to figure out. So yes, volcanoes matter, heat flow matters, yeah. Anne. Okay, so the question was, this Thwaites Glacier project is international, and so we had these 8 projects. How did that work? Was like one project American, one project Korean? So for the original 8 projects, one of the criteria was that you had to have 3 PIs from the US and 3 PIs from the UK. And then the division of labor, or hopefully what you did is you tried to find expertise that complement each other across the 2 countries. And so for the project I was involved with, it was primarily UK, US, but we also had German colleagues. And so every project was international. And then I think then part of, again, part of the sort of led not by me, but this collaboration had a DEI council, is just thinking about how you, ahead of time, especially with students, because it's things we didn't do 15 years ago. Let's be proactive and be open and communicate. What is it? How are our authorships going to be determined? You have these large international collaborations with 25 people. How is data going to be distributed? I mean, I think just being it's not hard, it's just being thoughtful and just having deliberate discussions about where everybody fits into the conversations. And I think for me, I think one of the maybe I think good things about Zoom, the COVID world, is that we all got really used to, I think, communicating over Zoom. So I think it's no longer everybody, like having Zoom meetings where you discuss different aspects, so that I think has become much easier. Like I didn't go into the field for this project, but just in the past, when would have gone to the field, right? You would have just shown up in New Zealand, you'd met people from other parts of the world, and then you get on an airplane and you go to the middle of nowhere. And you would have never actually talked to anybody about it. And so just having very deliberate pre-field deployment discussions. And then, of course, I think apparently generators was a nightmare, having people come from the UK and the US, but there are challenges because we use different plugs. So then there's always troubles having international collaboration. So for all the field camps, I'm not joking, there was the American generators and the UK generators, so that you could charge your laptops and everything. Anyway.
John from Oregon asks, could you comment on the effects of isostatic rebound on the dispersal and retention of ice melt?
Of course. And if hopefully okay, you said it, so I don't have to repeat it. Everybody heard it.
You got it.
All right. So the question, of course, was about isostatic rebound. And so hopefully, knock on wood, one of my projects currently in the current NSF Nether is actually in Greenland. And we've done some of this work in the Antarctic as well, but basically in both places, basically, as everybody knows who lives around here, hopefully, is that the ice advances, ice depresses the solid Earth. When the ice goes away, the ice rebounds back. And the rate at which that happens is based on mantle viscosity. So here's another link. So we could just talk. I mean, you could have an entire class on geology and ice sheets. So basically, how fast the ice wants to rebound is set by mantle viscosity. So if you want to understand the Antarctic ice sheet, you have to understand what's going on hundreds of kilometers below the seafloor, the bottom of the ice. And there are places in Antarctica, like the Thwaites Glacier, for example, where you have again, this comes back to the heat flow volcano question. It's an old rift. You maybe have a very thin lithosphere, so you actually may have a very low viscosity upper mantle. And so actually what can happen is your mantle is so responsive that as you retreat, you can actually slow down the glacial retreat because the ice, the bedrock wants to come up fast enough to help the ice sheet come up out of the sea level, out of the sea to a certain extent. So yes, mantle viscosity, GIA, it's all quite important. Next talk. Yes?
Great, thank you, that was really interesting. I was just curious how static or dynamic the sediment distribution is under ice sheets, and I imagine it changes relatively rapidly. You have to do this over and over to get better information, or just how is that affected?
Yeah, so the question was basically, we have all this dirt under the ice, or places where there isn't dirt and sediment, right? And we've just said how important having this wet, gushy sediment is to letting the glacier so fast. And the question is, how static is that picture? Is it dynamic? And the question is, it almost certainly is dynamic. And the thing is, these measurements of topography are so hard to get. There's only been one really good study where somebody's been able to go and redo it. They actually redid a seismic survey on the Rutherford ice stream in West Antarctica. And what they did is they saw over the course of a decade, they did like a 20-kilometer profile. I can't quite remember, 12 miles. And under 2 kilometers of ice, and like 90% of it looked exactly the same. Because it wasn't really what they were just, they just wanted to confirm, because they were doing a drilling project, and they just wanted to make sure they were confirming where they wanted to drill their hole. But they noticed like a drumlin appeared. That wasn't there 10 years earlier, it was like a little baby drumlin. But yeah, so I think and then we have some other data I could have showed from Thwaites where we see like crag and tell features. So clearly sediment's being eroded and deposited, and I think the time scale of that is, probably the best places to study the timescales of this is actually places like Iceland and things, where I think people are doing some really neat work, where you have recently retreating ice margins. And yeah, but it's almost certainly happening under the ice. But Antarctica is different because you're not getting surface water down, so things are a little more stable than in like Greenland and alpine settings.
One more? Way in the back there.
Paul, I was talking about this in my class this week about geoengineering solutions, and some scientists that have proposed the curtain to try to keep the warm currents from getting near the ice edge. I was just interested in your thoughts.
I can't hear that question. I won't respond, so I can't. So Susan asked a very, I don't know if it's controversial question or not, or something I don't know if I want to go on the record for, but I'll do my best to sort of not pin myself in a corner. So increasingly there's a segment of the glaciological communities coming up with these ideas of, can we geoengineer our way out of a collapsing ice sheet? And so there are a couple of ideas for that. And as we talked about today, one of the ideas we talked about is, the ocean. The ocean's getting in there, and that warm water is eroding the ice from underneath. What if we just put up this big curtain? This is a real proposal. Can you put in big curtains around the continental margin to stop water from flowing under the ice shelves and melting the ice? And this would almost certainly, if this was to happen, it would cost trillions of dollars, and it would be decades from now. So that's one idea. And then there's an idea that we talked about, is that there's all this water under there, and that the glaciers can go fast because there's water down there, and it lubricates, and they can slide over the bed. And so another idea is you drill a bunch of holes in the ice, and you just suck the water out, which also would have to be really expensive and really logistically challenging. And then basically the ice would be froze to the bed. So there are we're starting the community is starting conversations on the feasibility of these, and I would say that there's very strong opinions inside the glaciological community about the sort of whether or not these are things we should be talking about or not. And yeah.
Hey, let's thank Paul one more time for an excellent talk. Thanks, everybody. We'll see you in April. See you in April.
Pump the water back onto the surface and it think about the ice skating though. Dude, it'd be so fun.
Totally free to do anything. Okay. Thank you, everybody, for joining us today. That's the end of the live streams for more than a month. Plenty of me from my office, but we wrapped up the Cascades A to Z live stream series yesterday. And these live streams will not be happening until early April. We were all set to go with a visiting geologist from Spokane, but I got an email from her this morning that she's not allowed to travel. So we had to cancel her talk. We are hoping that we can have other people travel and join us and give these science talks. So this is an unusual time that we are all experiencing at the moment. I thank you for your attendance here. I did notice things got a little wild in the live chat. I chose to keep all of that. It's fine to disagree in the live chat as long as we're respectful, right? We can have different opinions, but it has to be respectful. And that's the only requirement, participating in the live chat with these programs. Very good. Everybody's anxious, it sounds like, to get outside and enjoy the beautiful spring weather here on the last day of February 2025. So, thanks everybody. I love you and goodbye from Ellensburg, Washington, USA. We'll see you in April. Goodbye.